wanted to start this off with some interesting statistics. Did you guys know this? Did you know that 3.14% of all sailors are pirates? Interesting. Some of you are going, what? This next one's for you. 4 out of 5 people don't really understand jokes about math. All right, let's get right down to it. The segments of chords theorem. Now this whole lesson is really about segment length. So we're going to move away from the angle measures and look at lengths of segments. In this case, chords. When 2 chords intersect in a circle like they do right here, then the product of the segment lengths, so think about multiplying with products, the product of the segment lengths of one chord is equal to the product of the segment lengths of the other chord. What? What am I talking about? All right, let's break it down. So we're looking at the pieces of the chords, this segment and this other piece of it. Let's call those pieces A and B. That's the segment lengths of one chord. The other chord, we might name like parts of this C and this part D. If we multiply the segment lengths of one chord, so that would be like A and B, and those get multiplied, then they're going to equal the segment lengths of the other chord also multiplied. We want that product as well. They'll be equal. They'll be equal every time. So the pieces of one chord multiplied together equal the pieces of the other chord multiplied together. Let me show you with an example. We're going to take these 2 pieces of this one chord. So 10 times 6, we multiply those together. That's going to equal the pieces of the other chord multiplied together. So that's 12 times x. Those are equal to each other. We're looking at 60 equal to 12x. So finding x would just be dividing by 12. X is going to be 5. That's about as easy as it gets. This next example isn't any different. We're going to, again, multiply the pieces of one chord. In this case, it's 10 and x, so multiply together. Set them equal to the pieces of the other chord, the 16 and the 15, multiplied together. Okay, so we've got 10x. That's equal to 240. And so dividing by 10, our x here is 24. Again, how easy is this? Now the secant-secant and the secant-tangent theorem is a lot like the chords theorem, only this time because they're secants and tangents, the intersection is going to happen on the outside of the circle. So you want to look at where your vertex is again. We're on the outside of the circle in both cases. Now this is a mouthful. I'm going to read through it. Let's see if we can get through it and then break it down. It says if 2 secants or tangents intersect outside a circle, the product of the entire segment length and the external segment length of one is equal to the same product for the other. So some key things in there. We're doing products again, so we're still multiplying. And we want to take a look at the entire segment length as well as the external or the outside segment length. Okay, so in our picture, the entire segment length, of course, would be right here. Let's label that as A. And the external segment length would be here, and let's label that B. That's what we're going to be multiplying together. Where is it on the other secant line? Well, again, here's the entire segment length, and here is the external segment length. So let's say the entire segment length is C, and the external part is D. We multiply those together. So we're going to say A times B is equal to C times D again. And what it boils down to is this. You're going to take the whole thing times the outside part and multiply them together. And that's equal for the other secant or tangent as well. Now it's a little bit weird with a tangent because, well, let me show you why. Here's a secant line. So this secant's just the same. Let's say the whole thing is A. And this external piece, there it is, on the outside is B. But when you look at the tangent line, it comes out to your point of tangency there. Here's the whole thing. So that's C. And then the external part, or the part on the outside, that's D. And you'll notice C and D here are equal. That's because it's a tangent line. And so that's going to be unique. Walking through an example. Let's see if we can find the pieces. What would we look at first of all for this whole thing? Well, it's made of 2 pieces, 5 and x. So I'm going to call the whole thing 5 plus x together. And of course, our external part is just the 5. So as I set this one up, I'm going to say that's 5 plus x for the whole thing multiplied by the outside part, which is just the 5. Now that's equal to the same property for the other secant. The whole thing we need to say is all of this together. So 6 and 4 would make 10. And then we're going to look at the exterior part is just 6. So this is 10 times 6. All right, if we just work the algebra through, I think we'll be good. So let's distribute the 5 into the parentheses. This is going to be 25 plus 5x. And this on the other side, we've got 60. And you know how to do the rest of this. 5x alone would be 35. And then dividing by 5x is going to be 7. So let's check that. This is 7. This one's going to be 7 plus 5, or 12. So does 12 times 5 equal 6 times 10? Sure enough. 12 times 5 is the same thing as 60. It's a 6 times 10. So that checks. All right, so x is 7. Here's a chance for you to see one with a tangent line. So let's take the secant first of all. Whole thing is what we need. What's the entire length? We're going to have to add up the two pieces. So we have x plus 5 plus 12 more, or a total of x plus 17. And then our external piece is the 12. So that first part is going to be x plus 17 multiplied by 12. And if you don't care, I'm going to multiply the 12 in front because that's usually where we put those single terms. All right, same for the tangent now. Here is where we see it weird. What's the whole thing? 18. And what's the outside part? Well, it's just another 18. So this is just going to be 18 times 18, or 18 squared. Maybe easier to say it that way. Okay, so now we just simplify, distribute that in. So 12x plus 12 times 17 is 204. And set that equal to 18 squared, which is 324. And let's just solve this out. So 12x would equal 120. And that's easy. X is going to be 10. Okay, those are the theorems, and those are pretty simple examples. They do get a little tougher. Let's look at one with a word problem. We're going to have to think a little harder on this one. So, you know, when you see a rainbow, it is really a part of a whole circle, and I don't have enough space to draw the whole circle, but let's draw a sample of it. So if we had the whole circle, we would only see the part that's above the horizon, and this is 5 miles across the horizon, and the 0.7 miles that we see above the horizon right there. So let's just sketch that in our picture. Now the 5 miles has actually been chopped in half. Did you guys see the right angle right there? And that means that that chord got bisected. So let's put 2.5 instead of the 5 miles, and another 2.5. Now the question here is asking us to find the radius of the circle. So we have the center, and we know that this, because of that right angle again, we know that this piece goes through the center if we extend, but we are asked to find the radius, which we don't know. So what I suggest we do is we use our chords theorem, and let's find some segment lengths that we do know. Let's find the other piece of this chord. I'm just going to call it x for right now. Okay, so the two pieces of this chord are 0.7 and x. We'll multiply those together, and that's going to equal the two pieces of the other chord, 2.5 times 2.5. All right, so we've got 6.25 on this side, and if we divide by that 0.7, x is going to come out to be, and I'm going to probably round this, so about 8.93. Let's make this approximate. 8.93 right there. Now, that is actually going to help me get my radius. Think about what we know about a radius. We've got two radii. Let me highlight. What does all this tell me about my diameter, the whole thing? We know the diameter is going to be just adding this little 0.7 above and this 8.93 that we got below. So let's say the diameter is 0.7 plus 8.93, which comes out to be 9.63. And therefore, the radius is just dividing that by 2. So the radius will be divided by 2. Final answer of 4.815. And units, of course, miles. So that would be the radius of the rainbow if we saw the whole thing. For our last example, I want you to gear up a little bit. The algebra could be a little bit intense here. So leave yourself some space. Don't write too big. We are looking again at just these secants. So this is where we're going to say, well, how long is the whole thing? And how long is the external part? And we'll multiply, like we saw in the previous example. So all of it together, 3 plus 5 is 8. And then our external, let's say that 8 times 5 is our first product. And then let's go to the other segment to see the other. to see the rest. So this whole thing, I want to add x minus 1 plus 6. So that's going to combine to be just plus 5. And then, of course, we'll use our outside or external part right there. So we're multiplying x plus 5 for the whole thing by x minus 1. And now you get to see why this algebra gets crazy. We're going to have to actually multiply, distribute this all out. Let's go for it. So x times x is x squared. And x times that negative 1 will give me a negative x. Next term is the 5x. And then this 5 times negative 1 is negative 5 at the end. And then we get to combine the like terms. So we have x squared plus a combined total there of 4x and minus 5. Now over on the other side, we just get to bring down 8 times 5 is 40. So this one ends up being quadratic, like we practiced. This has that squared term in it. We're going to have to get everything to one side and let it be 0. So let's do that by just taking away the 40 on both sides. And we'll say 0 is equal to x squared plus 4x minus 45. Now, the way I want to try to solve this is by factoring. If I don't need to do that quadratic formula, I'm not going to. So let's set up that magic x and see if we can find two numbers that work. Fill in your spots. So this is negative 45. We want to multiply to negative 45. And then bringing the 4 in, we want to make sure that these numbers add to 4. Can we think of two numbers that do that? How about 9 times 5 is 45? Now, of course, I'm going to have to make one of those negative, but I think those are going to work because I can see I can get a 4 out of it. Which one needs to be negative to make a positive 4 total? It's going to be the negative 5. Okay, those are two numbers, so let's break this up into its factors. We're going to have x in each of the first positions. We'll say it's x plus 9 and x minus 5 set equal to 0. So each one of those could be 0. X plus 9 is 0 only if x is negative 9. And on this one, x minus 5 is 0 only if x is 5. So we get these two answers. We're still not done because we don't know if both those answers work. Remember, you cannot get a negative length, and that you might be facing a negative length if you look at the picture itself. So x is negative 9. Does that work? If we plug in negative 9 minus 1, we're going to get negative 10. Negative 10 cannot be a length. So we're going to cross this one out. It doesn't really work for our picture. How about x is 5? Is that going to cause any issues? And it doesn't. I've got 5 minus 1 is just 4, and I can be 4. LM is 4. And that's actually the question. So we just answered it. LM is 4. So watch out for those quadratics. You may have to factor. You may have to do quadratic formula. In fact, there's a hint for your try this question. All right, give it a shot. I'll see you in class.